Hi, everybody, and welcome to Chapter 3, Section 4, and this is substitution. We do need substitution when we want to find integrals. We don't have many integration rules. For quite a few of the problems we see, the rules won't directly apply. We'll have to do some algebraic manipulation first. In practice, it is much harder to write down the antiderivative of a function than it is the derivative. In fact, it's really easy to write a function that doesn't have any antiderivative. We'll learn the basics. We won't do anything too complicated. When you find the derivative of a function using chain rule, you end up with the product of something like the original function times the derivative. So you remember, if we want to take the derivative of the composition of two functions, take the derivative of the outside function times the derivative of the inside function. Now, how do we get it into an integral form? Remember that when I want to undo a derivative or use the inverse of it to cancel the derivative function, I use the integral. If I take the integral of both sides, now on the left side, the derivative and the integral cancel, and I end up with f of g of x. And on the right side, I have the integral of f prime of g of x, g prime dx. We have our first function to integrate. It's x divided by the square root of 4 minus x squared dx. I don't see that formula anywhere here. We're only going to be using these integrals. What I do know is that if I were to take the derivative of just that function, the derivative of the square root of 4 minus x squared dx is equal to the derivative of 4 minus x squared to the 1/2 power with respect to x, or 4 minus x squared to the 1/2. I'm going to use the chain rule, which says I bring down the 1/2. I take 4 minus x squared. I subtract 1 from the 1/2. I get minus 1/2. Then I multiply by the derivative of the inside function, which is 4 minus x squared, or minus 2x. Well, let's simplify this. This 2 cancels with this 2. I end up with negative x divided by the square root of 4 minus x squared. Well, that's really similar to what I have, isn't it? Now that I have an idea of what's happening, this x is coming from the derivative of the inside function. I'm going to let u equal 4 minus x squared. The derivative of u with respect to x is equal to minus 2x. Also, I can solve for dx. I can say du is equal to minus 2 times dx. Multiply both sides by dx. This would cancel, and I would end up with du equals minus 2x dx. If I want to solve for dx, I would divide both sides by minus 2x. This would cancel, and negative du over 2x is equal to dx. I'm going to substitute. I have the integral of x divided by the square root of u. Dx is equal to du divided by minus 2x. The integral of negative 1 over 2 times the square root of u du. Now we can use our constant times a function to pull out the constant. The constant here is, this equals negative 1/2 times the integral of 1 over the square root of u. And that's equal to negative 1/2 times the integral of u to the minus 1/2 power du. I know how to integrate this. I use the power rule. It says n can't be negative 1, but our n is negative 1/2. Therefore, this is equal to negative 1/2 times u to the minus 1/2. I add 1, becomes u to the positive 1/2, divided by 1/2, plus some constant. This is equal to minus 1/2 times u to the 1/2 power, and divided by 1/2 is the same as times 2 over 1. This 2 cancels with this 2. I get negative u to the 1/2 power plus c. And then I go back and I see that I named 4 minus x squared u. I want to go back to my x. So I go back here and I plug it in. This is equal to negative the square root of 4 minus x squared plus c. And that would be my final answer. And if I take the derivative of this, I will have my integral. I'll have what I began with. And you can check it out. And again, we have something that we don't have the formula for. But I look and I notice that I have an e to the x plus 15. And if I think about the chain rule, the derivative of that is e to the x. That's where that's coming from. If I can understand that part, that means I can say u is equal to e to the x plus 15. And then again, I can say du dx. But instead of doing that, we're just going to say the derivative of u is equal to the derivative of e to the x, which is e to the x. The derivative of 15 is 0, and I'm going to put my dx here. So du is equal to e to the x dx. So there's 2 different ways to look at this. One way, this right here, is the same as this right here, which equals du. I have this e to the x dx is equal to du. And e to the x plus 15, we said is equal to u, and that's to the 3rd power. I have the integral of e to the x times dx, and dx is equal to du divided by e to the x. That whole thing is divided by e to the x plus 15 to the 3rd power, but e to the x plus 15 we already said is u. So this is u to the 3rd power, and notice this e to the x cancels with this e to the x, and I end up with the same integral of du over u to the 3rd power. Either way is fine, whichever way you like. Now, This is easy to integrate. This is the same as u to the minus third power du. When I get to a place where it's easy for me to take the integral, that means my substitution worked. So here I would add 1. This would become u to the minus 3 plus 1, or minus 2, divided by minus 2 plus c. This is equal to 1 over negative 2 times u e to the x plus 15 squared. This is really the same as 1 over negative 2u squared plus c. And so you can see the substitution makes things really a lot easier. Things that we wouldn't know how to integrate, with substitution, we can make it easy to integrate. Again, I look at this and I can't integrate just this, because remember, we're always compensating for the chain rule with the derivative. So if I take the derivative of x to the third plus 5, I'll get 3x squared, but I can handle the constant. Let's let u equal x to the third plus 5. And you'll see right away if it doesn't work out. Then du is equal to 3x squared dx. And the 5 goes away because it's a constant. Well, I have x squared dx, so I can just divide both sides by 3, and now I know x squared dx is equal to du over 3. That's again one way to do it. So x squared dx is equal to du divided by 3. We know that x to the third plus 5 is u. This becomes 1 over u. I'm going to take my constant out of the integral, and I get the integral of 1 over u du. The integral of 1 over u du is ln of the absolute value of u. We're going to always add our constant in. And now I'm going to change the u back to x's, and I get 1/3 times the natural log of x to the third plus 5 plus c. Now this is b from that last problem, and the only thing that's different here is that x cubed plus 5 dx is over x squared. If I made my u equal to x to the third plus 5, my derivative would equal 3x squared dx. But that x squared's in the denominator, so that doesn't really work. And it wouldn't work for me to say u equals x squared, because the derivative would be 2x dx, and that's not what I have in my numerator. So you can't always just jump into things. You have to think about it a little. I look at this now and I say, oh, I have an idea. This is really the same as x to the third divided by x squared plus 5 divided by x squared dx, which is equal to the integral. X cubed over x squared is just x dx plus the integral of 5 over x squared dx. Well, this is an easy one, so we're done. When I get to the point where I don't need any help, I can figure out my integral, then I don't have to do substitution or anything. Now I have a 5. I can take that outside the integral sign, and I end up with 1 over x squared dx. This is equal to the integral of x dx plus 5 times the integral of x to the minus 2 dx. Now, these are both just power rules. This is equal to x squared over 2 plus 5 times x to the minus 2 would be x to the minus 2 plus 1, or x to the minus 1, divided by minus 1. And don't forget we have plus c. If I simplify this, it becomes x squared divided by 2 minus 5 divided by x plus c. And this would be my final answer. I didn't need substitution this time. I just needed to separate this into two fractions because the numerator had a higher degree than the denominator. The denominator has a higher degree than the numerator. So they're different problems, similar, but different enough that they're completely different ways to solve it.